And let us now continue our sessions in the morning. Now, in this session, of course, you should continue to sit now during my sessions. Do continue to sit group wise because we will be having these exercises of discussion. So, please, you can rearrange yourself according to your group again. So, we will be doing a lot of these exercises where pedagogical exercises where we discuss. And of course, we should also discuss with other groups, but at least let one group mature. In this session, we will be looking at physical systems, right? We will be looking at physical systems, and I want you to give me examples, and I also discuss examples of physical systems where we can identify the properties that you talked about. So, we had identified several properties, you had in fact listed out several properties. We will of course see, we could discuss those properties in abstract form, but my concern is that in many institutions, the students don't sync themselves with the abstractions. Very often the student does not appreciate why we are discussing abstractions like linearity or shift invariance or stability and so on until they can associate those ideas with a physical system. So, let us discuss some examples of physical systems from different disciplines of engineering. That is also wonderful. It's not just for electrical engineering that you have systems. You have systems in electrical engineering, you have systems in mechanical engineering, you have systems in civil engineering. In fact, in mechanical again, there are the so-called mass spring-like systems, and there are also, as somebody suggested, thermal systems, so you can think of thermal systems either coming from mechanical engineering, or you could think of them as coming from, say, aerodynamics or coming from any other discipline, right? Thermal. So, in that way, the context in which you can apply the principles of signals and systems is very vast, is very broad. And that is why many a time the course on signals and systems is not only useful to the electrical engineer or to the electronics and communication engineer. You will find that students of other disciplines will also be interested in doing this course, right. So, we should appreciate and we should also see that breadth. Now, what is the intent of the lecture, to this current lecture? The intent is to understand two things. First, system modeling. And second is what is called abstraction. System modeling means describing the system, right, in a way that can be analyzed mathematically. That is what system modeling is. Creating an equivalent of the system which you can analyze on with pen and paper. That is system modeling, right. Abstraction means taking out of the situation what is common to many situations. So, we will understand the reason for abstraction. What is the need? See, we often wonder why we should be dealing with the abstract rather than look at the concrete system. The reason is very simple. If you have understood your abstraction properly, you can deal with more than one situation at once, right, and we will appreciate both of these things as we go along. Now, let us take system modeling first, right. Let us in fact look at two different systems which we'll find have the same system model, right. Let us take a simple resistor and capacitor in series. This is very familiar to us, it is an electrical system, right. Let us also take a mass, okay, acted upon by a force, but the mass is moving in a frictional environment. okay, and we will assume that the friction that the mass, frictional force which the mass experiences is proportional to the velocity. Now, you can have different models of friction, but we will take a model where the frictional force is proportional to the velocity, right. Now, let's look at this. First, let's model this. This is very easy to model. So, let us look at the voltage across the capacitor, right, and this is V in T. Very simple, let us write down the equation, right. The equation is, so see what is the current? The current is of course V in T minus VCT, and the current divided by R, the voltage divided by R, and this is also equal to, you can write in terms of C dVCT dt. Is that right? It's also the current in the capacitor, right. So, this is the, therefore, V in T is VCT is, well, V in T minus, you can write it down, is equal to RC dVCT dt plus VCT. Is that right? This also has the dimensions of voltage. This is also the dimensions of voltage, right. So, this is the model. So, this is the first order differential equation that describes the system. Now, I want you to do the following. Here again we will do a think, pair, share exercise. It will be a shorter exercise. I want you to consider a force being applied to the mass, and the force causes two things to happen to the mass. One is that it overcomes the friction, and secondly it accelerates the mass, right. So, the force has to be used for two reasons. It has to overcome the friction the mass suffers from, and it has to accelerate the mass, right. I want you to write that equation. I want you to take this model of the mechanical situation and write an equation which is similar to this equation. We will see the similarity of the two situations. So, first you can do a think, take only 1 minute to think and see if you can do it. Then you do a share for 2 minutes, and then do a pair, that is you discuss in your group, and then I would like you to share, right. So, one minute you do it yourselves. Till that time don't discuss, try and think yourself. So, I want you to model this in a manner similar to this, right, noting that the mass suffers from friction and the friction is proportional to the velocity. See, you can remember that the frictional constant may not be the mass itself, it can be some constant. So, you say the frictional loss due to friction is proportional to the velocity. The proportionality constant can be something, you decide, call it something. Okay, now you can take 1 minute to think yourself. So, maybe you can discuss in your group for about 2 minutes, and at 15:42 we will do a share in 2 minutes. Or what you can do is, when any of the groups is ready to share, you raise your hands. You are ready? Oh, wonderful, great. So, one group is ready to share. At least one group is ready to share. So, if at least 1 or 2 groups should have ready to share, then 2-3 groups should have, then we will share. So, I want you to see how there is a similarity between the two situations. A similar model will describe both of them. So, whenever any group is ready, please raise your hand. One group has raised its hand. You ready? Oh, very good. So, 2 groups are ready. One more group ready, very good. About 3-4 groups are ready, we will share. So, how many of you are ready with how many groups are ready? Oh, very good. Good. Great. I think several groups are ready. So, let us now have a share round. Yeah. Maybe would you like to come and share your solution? Yeah.
So the equation is F is equal to M.
Why don't you write? Minus, okay,
Mu
minus
V
or plus?
plus.
Plus, because it overcomes
Okay.
the two components. No?
Yeah.
Very good, that's correct. That's how many of you? So now you can explain what you're.
Yeah. So here this mass is like a capacitor because like energy is there. Yeah. So here our resistance is the friction is like a resistor. So because it is resisting whatever force we are applying. So we can take that analogy here.
That's very correct. So in fact, now you see the similar. In fact, you can make the equations exactly similar. Yeah. Thank you very much. So that's very correct. In fact, if you look at now, do you all agree with the equation? Essentially, there are two components that the force overcomes. One component is meant to accelerate the mass. So that acceleration is proportional to the mass, right? So whatever part of the force is available to the mass to accelerate it, that causes m dv dt, right? That's v is the velocity of the mass. But the moment the mass starts acquiring velocity, it suffers friction. And how much of friction does it suffer? Frictional cause some mu times v, right? So you can rewrite this as F by mu is equal to m by mu times dv dt plus v, right, where v is the velocity of the mass. So that's very similar. So F by mu can be seen something like v in t. It's like an input which you're giving, right? So you have to think of now here, the way you should think of it is that it's not the force which is the input, but the force divided by the frictional constant which is the input, and that is an equivalent input which accelerates the mass with m by mu, and then it also actually the force divided by mu has the dimensions of velocity, right, has the dimensions of velocity. So as you see, these two equations are very similar, right? And now that means, what does it mean? It means if I am able to solve this equation, I can also solve this equation. If I have a way to solve that equation, a method to solve that equation, it also helps me solve the other equation. Now this is what is meant by, now both of these are examples of system models, right? Both of these are examples of system models. There are two different systems we have brought in here. One system is an electrical system and the other system is a mechanical system. But both of them can be seen to have a similar model. What is the beauty in this? It means that I can learn one tool and I can solve two situations. So now we come to the next point, abstraction. What is meant by abstraction? In fact, the word abstract. See, there are different words which have the root tract, For example, extract, abstract, retract, right? Subtract, right? These are all different roots. These are etymological examples of different roots which have the word tract in it, right? What is meant by abstract? Retract, of course, is to take back. Extract is to take out. Ex, in fact, means to take out. What is abstract? Now, yes, we can, what is abstract? What do you mean by abstract? See, when you write an abstract, you write an abstract for a research paper. Gist. Yeah, it's the gist. The substance, synopsis, the essence. That is the abstract, isn't it? You abstract. Now, why do we abstract? And what is the advantage? Why we are discussing this is because, see, I know we can start writing equations. I know that all of you will in a jiffy tell me the solution of this first order equation. You are all, from electrical or electronic background. It does not require a lot of, it's not rocket science to tell me the solution to this first order equation. That in the class you will tell. But in the class, very often, The student is wondering, why is my professor going on talking about linearity, shift invariance? Why is the professor going on talking about differential equations? Where does this connect with real life? Not only that, that is okay. You can say, oh, this equation connects with real life like this. But then why do we study a course like signal systems where, in the textbook it all seems like those are, hi-fi things which have nothing to do with reality. What is the connection between, why do we need to abstract things in such a way that we separate it from the physical situation? That is what abstraction means. Separating also from the physical situation, right? Now, I have actually given you a hint. I want you to take again, now this time we will do a think, pair, share, but this time very quick think, pair, share, because a simple question. What are the merits of abstraction? So, you first take only half a minute and think, right? Then you take 1 minute and pair and discuss in your group, and then we will share what you have come up with. So, now start, half a minute only to think. Yourself, don't talk when you are thinking, you think for half a minute, then you pair, then you discuss in your group. Everybody is in a big hurry to pair, but you should first think, otherwise you don't pair successfully. So take half a minute to first think, reflect. You should learn to think and reflect, otherwise everybody is in a hurry to pair because it's easy to do. Let's get used to this think, pair, share, you should get used to it. It's a good thing to do in the class. What are the merits of abstraction? That is the question. Wait, let's have, so this is a quick think, pair, share. So you have half a minute to think, 1 minute to pair, discuss, and then raise your hands when you're ready. Okay, how many of you are ready? Share. Very good. Okay, let's have a share. We'll give a chance to a different, would you like to come and share this time? Yeah.
Yeah, abstraction, what do you mean abstraction? Means the whole essence of the thing, the analysis or the system. What is the system is going to be, what is its characteristics, what the elements are being used. If you look at the abstraction, you can get an idea what is about the system about and what is in what way it is going to be. If the abstraction is read it properly, then the same thing can be percolated in a similar way in the similar system. Okay, so no need to go in depth into the system, but the abstraction, the gist of the system you got to know, then we can utilize the same meaning into the similar kind of systems. Yeah, that's the abstraction.
Very good. I think that's a very good answer, but we'll give one more chance. Anybody else who wants to, see it? Any other group wants to share?
Rafram, I'm Shamim Ahmed. So I have 3 things in mind.
Yeah.
First is that we can get the gist of the system.
Yeah.
So we can better understand the inherent properties of the system by using abstraction method. Second thing is we can apply it to similar systems. Okay, so we won't have to analyze a different system thoroughly.
Correct.
We can just apply these abstraction to that, and those will work for that too. And the third thing is we can put it into a computer and simulate it to get the results without using actual physical systems.
Very good.
Thank you.
Very good. I think we've got some very useful responses here, isn't it? In fact, what are the common things that have come out, which both the speakers just said? In abstraction, you have 2 advantages, or rather 3. One advantage is many at once. Many systems at once. The same abstraction is relevant here and also here, right? So, many at once. Learn one, get many, or see, there is, if you look at all businesses, they keep tempting you with saying that buy one, get one free, isn't it? So, same thing is happening here. You learn one abstraction and you get many systems free, right? So, the many for one, that is one thing. Secondly, what is the reason why abstraction is important? It allows you to use tools. as Shami Ahmad said, isn't it? It allows you to use tools. So, you cannot, if I have to start connecting a resistor and capacitor and finding out, then it's going to be, I need to go to an electronics lab, or I need to set up a breadboard, or if I want to connect a mass and start experimenting with frictional forces, it's going to require a setup. But if I can abstract the situation, I can use a computing tool to come out with a solution and with an interpretation. So, use of tools which can apply to more than one situation, and the use of more convenient tools, right? That's another reason for abstraction. The third reason is also being able to extrapolate. Right? See, I have this situation. Suppose I had a slightly different situation, I don't need to go and set up the new situation. If I can see the new situation in terms of my abstraction, I can predict what will happen in the new situation. So, I can extrapolate, I can look beyond what the current system is. That is also an advantage of abstraction, right. So, when the student looks at you and says, why are we learning these abstract concepts? You should be able to explain. This is the reason why we are learning these abstract concepts, right. So, when you, in the first module in signals and systems, when we talk about systems in their natural domain, we have to also bring in this idea of abstraction. Why is abstraction important? Why is modeling important? And when you are modeling, then of course you are bringing in system properties, right. You are bringing in system properties. So, now let us talk about system properties. Let us now come to a more formal definition of system properties. Now, yes, sure. Abstraction, that's a good question. The question is abstraction also just system modeling? So, the answer is that abstraction is one level above system modeling. So, now for example, here I had two different system models, but out of them I could abstract a situation that, you can say yt is equal to xt plus alpha times dxt dt. This is the abstraction. But for the RC circuit case, yt is equal to the input voltage, xt is equal to the capacitor voltage. Or maybe, okay, I can see, yeah. And of course, alpha is RC. Now, maybe actually I should, if I want, now, very often, maybe here I have used the wrong terminology, because very often we like to think of yt as the output of the system and xt as the input of the system. So, maybe I will interchange here. I will say xt is equal to yt plus alpha dyt dt. Okay. So, I would, because we often want yt to be the output of the system and xt to be the input of the system. So, here we think of the capacitor voltage as the output of the system, right, and the input voltage as the input to the system. So, therefore, I should write the equation like this, right. Now, in the RC circuit case, it is this way. In the mass friction case, what is the situation? The input is F by mu. F by mu is xt, isn't it? And yt is equal to the velocity. right? Velocity of the mass, right? And of course, alpha, what is alpha there? M by mu. Is that right? M by mu is the velocity, right? Is alpha. So, abstraction is one level higher than the system model. Okay. Now, yes, coming to system properties. Let us now, you see, you told me so many properties in the morning, right? In fact, we'll recollect many of them, but you told me so many properties. You told me about linearity, you told me about shift invariance, you told me about invertibility, you told me about memory, you said, what are the other things you said? I mean, yes, causality or non-causality, then what else? Yes, shift variance, yeah, non-shift invariant, yeah, symmetry or asymmetry, what else? Yeah, static or dynamic, yes, stationary, non-stationary, you told me so many different things. Now, out of these we have to sift out which we really are going to call system property. For that we should first say what is a system property, again abstraction, right. So, we need to now we have so many, for each property you will start giving me a definition, but you must first tell me what is meant by a system property. Now, you have seen so many different system properties, many of you will also appreciate what they mean. But I want you, again we will do a think, pair, share exercise. This time only 1 minute for thinking, 2 minutes for pairing, and then we will share. So, 3 minutes. So, now 1 minute think, that time I should not hear any sound from anyone, right. You think yourself, tell me what is the meaning of system property, abstract, at the abstract level. How do you define a system property? So, this you must tell me, so and then explain with examples with the properties that you have studied, is that right? So, only 1 minute or maybe only half a minute to think, and then about 2 minutes to pair, and then raise your hands once you are ready to share. Okay, I will tell you when the half minute is up, then you can start pairing. Until that time, please don't talk. Think yourself. See, you must, why I am emphasizing the think, pair, share is, you must do this in your class so that your class is active. At the same time, you must make sure the think step is what most students will want to skip. Because they are lazy, you don't want to think yourself, you can always pair and discuss. So, you must ensure that you develop the habit yourself of doing the think step as well as you can. Because when you do the think step well, then you are also in a better position to pair and give something useful when you pair. And pair really means discuss in your group, doesn't mean exactly 2 people, but it means discussion. But to discuss meaningfully in your group, you should have first thought it out yourself. So, students are likely to skip that step, don't allow them to. Okay, we have not yet started pair. No, wait, I said I will tell you when the half minute is done. I will tell you when the half minute is done. So, give you a full effort to thinking. Okay, now you may pair for about 1 minute, 1.5 minutes. Before we start pairing, do you see, do you notice the effect of thinking? Can I have your attention? We will discuss the question later. But now, if you have done a sincere job of thinking, you see the benefit of that when you are pairing. Is that right? So, you must, yeah, please go on. So, teaching associates, my suggestion is, why don't you people sit with some of the smaller groups, so you can actually participate in the discussion with them, right? You can sit with some of the smaller groups, so you can distribute yourself and sit in different groups. So, which of you would like the teaching associates to sit with you? Raise your hands. You would like, so come, one person can come here. Now, which of you would like the teaching associates? Yeah. See, one of you can go there. Can go there. Can come there. That's it. And which of you would like the teaching associates to sit with you? Which group would like the TAs to sit with you? I have one more TA. You don't, none of you would like the TAs to sit with you? You want, yeah, okay. So you can work with that. Give me a broader definition of system property. What is a system property? Okay, raise your hands when ready. Very good. So we have, very good. So I think we have several people ready. Now whom can I give a chance this time? Yeah, please raise your hands who are ready. Why don't you come this time? Yeah. You're also ready? Okay.
The system property basically tells about the behavior of the system, and it also tells about the relationship between the input and output, how output is related to input. If I take a simple amplifier, I can say y of t is equal to g into x of t, where g is the gain. If we keep on increasing the gain, how output will be changing. So that is what the system behavior.
Thank you. Any other group which would, yeah, please.
The same definition, sir, but I want to modulate. The output depends upon the mapping rule of the input. Depending upon the different features, whatever rule we are going to apply, the output depends upon the input rule which we are going to apply.
Yes, any other group? Now, I want you to please listen to me carefully. See, I want you to now define, see, we are doing abstraction now. So, we had discussed several system properties. When we say abstraction, I want you to capture what all these system properties are in a meaningful definition. It should apply to all those properties, right? So, yeah, would you like to come? Yeah, okay, yeah, give them a chance. We would like, see, one of the principles in Think, Pair, Share is to give different people a chance every time, right? So, as far as that, yeah, please.
So, as per my knowledge, it shows the characteristics or behavior that helps to understand easily for any system.
Okay, very good. But true, that is all correct. But I want also an operational, when I want to define system property, I also now want an operational definition. How do I examine that system property? Mathematically, yeah, would you like to come? Yeah, sure. Okay, fine. Yeah.
System property is the property of the system respond for a particular input depending on the external conditions like time variance, time invariance, and all external disturbances taking into consideration how the system responds to a particular input signal and what type of output you are getting from the
Yeah, I can see you're all going in the right direction. But one thing, I told you, I also want to have a mechanism to examine the system problem. So it's not, again, I can say, well, the system is linear, the system, but how do I examine and establish the system is linear? I also want that idea to be captured in your definition of the system problem. Yes, come. Yeah, you can come and speak and share.
Just a simple example of a linear system. Suppose I have one simple DC source, and I have one R load, resistive load, and if it is linear, then if I increase my voltage in same proportion, my output should increase provided that resistance is same. Suppose we are calculating, suppose I, V by R, R is 1, so we don't need to bother about R. So if my V is 1, then I will get 1. If V is 2, I will get 2. If I scale V by 3, then my output will be scaled by 3. So this could be example of linear system.
Now this is one part of linearity, isn't it? Linearity has two parts. What are the two parts of linearity? It has,
instead of providing V1 and V2, I can
yes,
which is equal to V.
yeah. So
So
that's right. So linearity in fact has two parts, right? Linearity has additivity and homogeneity. What does additivity mean? It means if I test the, I took this because I want to try and help you answer my question, basic question. I take additivity. What does additivity mean? I perform 2 experiments on the system. I give it one input, look at the output. I give it a second input, look at the second output. Then what do I do the third time? I give the sum of the 2 inputs and I look at the output. When will I say the when will I say the system is additive? If the output is also the sum of those 2 outputs. Is that right? So additivity involves 3 experiments, right? In the first 2 experiments, I give it an input and observe the output, and in the third experiment, I prescribe the output for the input. That's the property, isn't it? What is the prescription? The prescription is if I give the sum of the 2 inputs for the property to hold, additivity property to hold, what is the prescription? The output must be the sum of the 2 outputs, and this must happen for any such pair, any such 2 inputs in the first 2 experiments. Is that right? Now are you getting where I am going for property, right? Now what is similar? Let's look at homogeneity. What is homogeneity, or homogeneity is also called scaling, right? The property of scaling. What does the property of scaling say? If I multiply, now again think in terms of experiments. So I give one input and I observe the output, right? Now what is the second experiment I do? I give a scaled version. I multiply that input by a constant and give it as an input. And what is my prescribed output? The output should be scaled in the same way. It should be scaled in the same way. So if I am scaling the input by C times, the output should also be scaled by C times. It is not enough for the output to be scaled by C squared times or something. Even though it will be scaled, it does not satisfy homogeneity. Is that right? So therefore, what is common now? Now I am helping you get to a formal definition of property. What is a system property? A system property is the prescribed result of a prescribed. So see, it's the prescribed. What are the system properties? Prescribed results, prescribed consequences of prescribed experiments. Can you see that? System properties are prescribed consequences of prescribed experiments. Now I want you again, think pair share once again. Now I have shown you how additivity and homogeneity fit this description, right? They are prescribed consequences of prescribed experiments. I want you to show me how causality, or rather how shift invariance, stability and causality are in the same definition. Now this time we will do a jigsaw, right? So we will use the technique called jigsaw, pedagogical technique. We will do jigsaw plus think pair share. See the technique, well there are different names, but jigsaw really means that I divide the task of learning in a group of people in the class, right? So I assign one part of the task to one group, I assign the second part to a second, and whatever number of pieces I have. So, I want to answer a bigger question. I do not give the full, see, it may be inefficient to give the task to the whole class, and also, it may be a waste of time. So, instead what do? I give one part of the task to one part of the class and so on, right, depending on the number of parts. Now, here I have 3 parts. What are the 3 parts? I have shift invariance, causality and stability. These are the 3 properties, system properties, where I want you to give me a definition in that language, prescribed consequences of prescribed experiments. So, for each of them you have to prescribe some experiments and you have to prescribe the consequences. Now, we will do one thing. So, groups 1 to 3 will take groups 1 to 3. Which are groups 1 to 3? Raise your hands. Yeah, all of you will take up the task of shift invariance. Groups 4, 5, 6, raise your hands, will take up the task for causality. And the remaining groups 7, 8, 9, 10 will take up the task for stability. Okay, please start. Think, pair, share. Now, initially think ekdam, I don't hear a word from anyone. Think for 1 minute. So, in thinking, all of you should see, do you notice, how many of you notice that when you do your thinking sincerely, the pairing becomes more effective? How many of you notice that? Yes, you notice that, right? So, when you do your thinking sincerely, the pairing becomes more effective. So, think sincerely for 1 minute. When you are thinking, don't talk to each other. When you are thinking, don't talk to one another. Just think yourself, otherwise the pairing will not be effective. We will do think for 1 minute, then pair for 2 minutes and then share. Groups 1, 2, 3, shift invariance. Groups 4, 5, 6, causality, and group 7, 8, 9, 10, stability. And then we will put the jigsaw together. Okay, think step is okay. Now you can do pair for 2 minutes. How many groups ready to share? Can you raise your hands? 1. Please raise your hands. How many groups are ready to share? 1, 2. Only 2. 3. Okay. Ready to share? Okay. Now, which group is ready to share about shift invariance? Please raise your hand. Ready to share about shift invariance? Okay. Come, any of you, maybe you have come before, someone else from your group. You also come. So, any new person from your group. So, you have to tell me the prescribed experiments and prescribed consequences. Shift invariance, anybody ready? Shift invariance? Okay, causality, anybody ready? Okay, come. Now, new person from the group. Okay, yeah, he can come.
Yeah, regarding like system properties, so prescribed consequences for prescribed experimentation. So let us take one example for causality, like clapping of hand. So when we clap, as our intensity will increase or decrease, accordingly the signal will be generated at output. The moment we will stop them, like output will be not there. Similarly, we can consider like CRO. CRO as a system, when we are giving input as a sinusoidal signal, it will appear. When we are giving triangular signal, square signal. So this may be considered as your for causality, causal system itself.
See, so I think you are referring to the idea of cause and effect, right? So you are saying that the cause is what? So he's thinking.
Like, so all prescribed experiment, the consequences are generated as per the experiment.
So no, I think I can see what you are saying. I think where you are coming from. What he's saying is that, the effect is a result of the cause. I appreciate that. So, what he was trying to say is that the effect, the causality in fact refers to the fact that the effect is a consequence of the cause. But I have a slightly different. See, I told you in additivity and homogeneity, I said prescribe these experiments, do this, and in general, when I want to define causality, do this, and this is a little difficult. That's why I am seeing if somebody has got it. So, do this, and and if this happens, then the system is causal, right? And this should be, again, it has to be an abstraction because it has to be applicable to all such systems. Is that right? Now, would somebody like to refine his understanding of causality? Okay. Okay, so only the fan starts running only after I press the button. So, there is a cause and effect relation. I agree. Now, can you capture this in prescribed experiment, prescribed outcome, prescribed consequence? Want to try? Yes, it has to be, it has to be abstract, right? It has to be beyond situation. Yeah. Not example. It has to be beyond situation. Yeah. You want to say? Yeah, come.
Can we take the example of capacitor charging? Like if you apply the voltage and initially capacitor is not charged. So, the further after applying the voltage, it will start charging. It depends on only the present input. But if capacitor is already charged, then the output will depend upon the present input as well as the previously charged on the capacitor. Can we take these examples?
Well, see, the example is correct.
Okay.
Example is okay, right?
Experiments.
Yeah, the example is fine. So, in fact, all your examples were fine. Her example and all the other earlier. In all these cases, you are talking about specific situations, right? Specific examples of where the effect is a consequence of the cause. I am saying, can you go beyond the situation? Yes, mathematically, how will you go beyond the situation? Yeah, want to try?
Suppose we can take one simple mathematical example of one system xt and plus xt minus 1.
Very good.
So, this is my simple system. So, suppose if I am taking t is equal to 1.
Let's take this
So
example.
t is equal to 1, then you can see that here it to y1, so it is depending upon my present input as well as my past input. So this is my causal system because it is only depending upon my present input as well as past input.
So again, you're going there. Now, you got out of the situation, you have come to something which can apply to many situations. Agree. Can we do even better? Yeah, okay, very good. Yes. So Shamim will come and do even better. Yeah.
We will just generalize it more. We will put as many variables as we can. Okay, so we will have yt equals to, there will be some constant, like it say c1, and here we will take another c2t, and then we will have c3 here, c3x, and c4t minus c5. So it will be a complete generalized equation. I may be wrong. Sorry, sir.
No, for example, no, good. It's interesting. But here, for example, let me give you an example here. Is this always correct as a causal system? Suppose C2 is equal to, yeah. Now let's take the situation where, no, it's good. You see, it's always good to, now suppose I took a situation where C2 is equal to C4 is equal to 1 and C5 is equal to minus 1. What will happen? There is a problem. No? That's enough. So suppose, for example, C2 is equal to 2. Is that okay? Xt depends, yt depends on x of 2t. That also is a problem. So where, so it's good. See, it's good to think like this. What happens is otherwise, you should ask these questions and, it's important to. Now, yeah, any more about causality? Anyone else would like to give a more accurate? It's a little difficult. That's why I'm a little difficult. Okay, let me give you the answer. Yeah.
Playing with that yt is equal to suppose xt square and all.
There's a problem, isn't it? There's a problem. So now can I give a definition of causality? What is the purpose in causality? The cause and effect, a lot of you are saying, the cause and effect relationship. The effect should not precede the cause. That's what you're saying. The effect should not precede the cause. Now, how do you capture this statement mathematically? How do you prescribe? So now I give you the answer. Let us perform two experiments on the system. So, I have to tell you in terms of experiment and consequence. No? So, what are the experiments? The experiment is give two inputs to the system. You have the same system. Okay. Give two experiments, give two inputs to the system and observe the corresponding outputs. But of course, there's a caveat on the inputs. The inputs are identical up to a particular time. So, here the independent variable has to be ordered. There must be a way of ordering the independent variable. Right? Time, of course, one-dimensional variables can be ordered. But if you have a two-dimensional variable, can I order it uniquely? There is no unique ordering, isn't it? So, there I have to fix an order then. So, I have to be able to, if I want to define causality, the first thing is I have to be able to order the independent variable. Once I have ordered the independent variable, then I can say if the two inputs are identical up to a particular value of the independent variable, which means for all values of the independent variable less than that particular value T0. The outputs, so this is the prescribed first set of experiments, right? And what is the next experiment? What is the prescribed consequence? Consequence is Y must also obey the same property. The output must have the same property. The outputs must be identical up to that point. Now, do you now think over it? As you have a cup of tea, you think over this, right? Does this capture all that you want to capture about causality? Totally generalized, isn't it? For everything. Does it capture everything that you want to capture about causality? If it doesn't, come and tell me what it does not. If it does, come and tell me that it does. Right? So, now we can all go for a cup of tea and come back by 4:45.